Hi everyone, in this video I'm going to go over how to find the pH of a strong acid, strong base titration. And this is the example problem that we're going to work through. So the first thing you have to be able to do when you read these problems is identify what type of acid and what type of base that you have, because that drastically changes how you solve them. And so we've got a 25 milliliter solution of HCl, which is a strong acid, and it was titrated with 0.5 molar sodium hydroxide, which is a strong base. And then we're told that it takes 35.6 milliliters to reach the equivalence point, and 40 milliliters of NaOH were added total. And so the first thing I want to do is write my reaction out. So it is HCl, which is a strong acid, plus sodium hydroxide, which is a strong base, and that's going to make H goes with the OH, so water, and sodium chloride, so salt. Salt is aqueous, and then because these are strong acids and strong bases, they're fully aqueous. When something is aqueous, it will fully dissociate in water, which means the ions separate. And oftentimes you might get asked to write the net ionic equation. So the net ionic equation gets rid of anything that is aqueous on both sides of the equation. And so chlorine is aqueous in HCl, which means really what it looks like is this. You have hydrogen ions and chlorine ions. We have sodium ions and hydroxide ions. And both the sodium and the chlorine ion, they stay ions in the product side. So I don't include them in my net ionic equation because they're ions in the reactants and in the products. However, water is not. Water is water, covalently bonded water. So that would be the net ionic equation. And so what's important about writing this net ionic equation is it allows me to see that for every hydrogen ion, a hydroxide ion is going to neutralize it. So it's a 1-to-1 ratio of acid to base. Now let's look at what do we have. So we're told that we have a 25 milliliter solution of acid, and it gets titrated with 0.5 m base. So I'm going to label that 0.5 m base. And to get to the equivalence point, you needed 35.6 milliliters of hydroxide. The equivalence point is when moles of acid that you originally have are neutralized completely by the moles of base you get added, or vice versa, depending on the titration. But these two are equivalent moles. And so anytime you have a titration problem, the first thing you want to do is go solve for, okay, how many moles are there? And you do that based off of the data from the equivalence point. So the equivalence point again was 35.6 milliliters of base, and the base was 0.5 molar sodium hydroxide. That is the first thing you always want to do. So 0.5 m NaOH equals moles of OH. And you don't have to call this NaOH, you can just call it OH because that's really what it is. Divided by 35.6 milliliters is 0.0356 liters. You multiply 0.5 times 0.0356, and we find out that your moles of OH are 0.0178. So how many moles of hydroxide were added to get this to the equivalence point? And again, the equivalence point is when moles of OH equal moles of H. So now I know the moles of hydrogen ions that were present initially. And I'm going to go ahead and write that underneath here. So this is always step one. Look at your equivalence point data, get your moles, and that will help you figure out what's going on. And so the first part of this question said, find the pH when 0 milliliters of base were added. So that is at the beginning of the titration when you haven't added in any base. So before I've added in any base, it is only strong acid. That's all that is present. Now, how do you find the pH of a strong acid? To get the pH of a strong acid, all you do is negative log the concentration of hydrogen ions. How do I know the concentration of hydrogen ions? For a strong acid, the molarity of the acid equals the molarity of the hydrogen ions, because a strong acid will fully dissociate, like we said earlier, or fully separate into hydrogen ions. So what was the molarity of my acid? We weren't told that. However, based off of the equivalence data, we know that because equivalence is when moles of OH equals moles of H, that I had 0.0178 moles of hydrogen ions. And so that's my moles, 0.0178 moles of H over the volume of the acid, because we haven't added any base yet. The only thing that's in your flask is acid. And my acid was 25 milliliters, so 0.025 liters. And that'll give you the molarity of your acid, aka the molarity of your hydrogen ions. And when you divide that, you get that it was 0.712 m. And so to solve for pH, all you do is you negative log, again, that molarity. So pH will be negative log 0.712. And that will give us a pretty low pH. But it's a strong acid, so that doesn't seem unreasonable, 0.147. So that's how you find the pH of a strong acid before you add in any base. The next part of this question asked, what about when 10 milliliters of base are added? And so I told you at the beginning to look at your equivalence data. So at the equivalence point where moles of acid equal moles of base, you added 35.6 milliliters of base. We're not at the equivalence point yet because we've only added 10 milliliters. And so you need to know that this is before the equivalence point, which means before the equivalence point, some acid is neutralized, but not all of it is. So we have excess acid right now. And it's an excess strong acid because that's what this titration is. And so what I like to do is let's rewrite the reaction. What are we reacting? We reacted hydrogen ions with hydroxide, and we're making water. The sodium and the chlorine don't really matter. And when this titration started out, we had 0.0178 moles of H. We've added in 10 milliliters of hydroxide. So we need to figure out how many hydroxide ions we added in moles. So I go back to my problem. The molarity of NaOH was 0.5. And so off to the side, I have 0.5 m NaOH, or you can just call it OH, moles, and I've added 10 milliliters. So 0.01 liters. So I added in 0.005 moles of OH. So looking at our balanced equation, this is a 1-to-1 ratio. Every 1 mole of hydroxide you add neutralizes 1 mole of hydrogen ions, and it'll make a mole of water. But we didn't add a mole of hydroxide ions, we added 0.005 moles of it. That means 0.005 moles of this were neutralized. So we have less hydrogen ions left. And so how do you figure out how much is left? You just subtract. This is the moles of hydrogen ions I had initially. And I'm going to subtract how many got neutralized, which is the moles of base I've added. And that tells me how many are left at 10 milliliters. And so that would be what? 0.0173 moles of H are remaining in this solution. Now the question wants the pH. This H again is a strong acid. pH for a strong acid is just negative log the hydrogen ion concentration. And that should say brackets. So I need to go find the concentration or the molarity of the hydrogen ions. Do that over here. Now, my moles of hydrogen ions that are left are 0.0173. And the volume, you need to think about when you did this in a lab. So when you're titrating, you have a beaker and you're adding in base. You would have a flask. The flask had 25 milliliters of acid in it, and you added in 10 milliliters of base. So the volume in your flask is not 10 milliliters and it's not 25 milliliters. It would be 35 milliliters because you need to add those volumes because that's what happens. And so you might want to make a note that you always have to use the total volume, which is how much acid you had plus how much base you've added in. And that'll give me the molarity of my hydrogen ions now, which is 0.494 m. Because it's a strong acid, I just negative log that number to get the pH right now. And the pH would be 0.306. If we check up above, before you added in any base, the pH was 0.14. After I've added in 10 milliliters of base, the pH has gone up. That would make sense. As you add in base, the pH is going to rise. So we probably did this question correctly. Now, the last thing for this video that I want to talk about really fast is the equivalence point. That wasn't one of the questions that we were asked to find the pH, but I think it's worth going over really fast. So when you have a strong acid and a strong base, the pH at the equivalence point, so when you added in 35.6 milliliters, that pH is 7 always. For a strong acid, strong base titration, the equivalence point, which again, equivalence point is when moles of H equal moles OH, your pH is always 7. In my next video, I'm going to go over how to find the pH if you added 40 milliliters of base for this problem. I hope this was helpful.